Hey everyone, and welcome back to PrepFusion. So today we'll start a new chapter, that is the controllers and compensators. So far we have been studying a lot of things, like we have studied how to analyze a system, how to analyze the frequency response, how to analyze the time domain response of a system. We studied all that. Now it's time to implement all those things what we learned. In controllers and compensator, what is the main motto? Here the main motto is we know whether the system is stable or not. We know whether the system is how is the performance parameter of the system. Now we want to improve it further, and we want to enhance it, and we want to make the system stable. For all those things, these two controllers and compensators will come in handy. Obviously, for understanding like how to improve the time domain parameters, obviously you have to understand the current parameters, what are the current specifications of the system. From that we can understand that how much do we actually need to improve. So for that, obviously we understood how to analyze the system. Okay, and now we will implement that. Basically, just wait a second, let me check if everything is recording or not. Yeah, everything is recording. So let's start. So this will be the lecture 1 of basics of controllers and effect of adding poles and zeros in the system. We learned about this in brief in the time response chapter, where we added open loop poles and open loop zeros in the system. Here we'll go in more details. Yeah, sorry, the video got cut for some reason. I was saying that do remember that this is a very important chapter in terms of interview point of view. This chapter and time response chapter are mainly asked if you say, like, you have to say your favorite subjects, and if one of those favorite subjects is control systems, then the topics, the hot topics are time domain analysis, time response analysis, and controllers and compensators, because that is where you get tested of your knowledge in the control systems. Okay, so these so for interview point of view, you can focus in these topics more like later after you get selected for gate, right, in IITs. Okay, so let's first understand what is a controller. Controller is a device connected in the forward path of a plant to improve the transient and steady state performance of the system as per the requirement. So it is a device that is connected, like here I have shown you the block diagram in the first chapter itself, that we connect the controller here to improve the plant performance, the transient and the steady state performance. So you know, now you know the difference between the transient and the steady state performance. Also, controller is a device that is used to improve the stability of the system. So obviously it comes under the steady state itself. Like if a system is unstable, then controller will help us make the system stable. Now input to the controller is the error signal. We have understood this concept with the steady state error part, where we studied the steady state error part. There was one controller sensor and the same block diagram was there. So input to the controller was always the error signal, and it will give the output according to the error signal. And obviously you have to design the controller in such a way that it will improve the plant performance and the stability. Okay, so all these things. So yeah, these are the brief overview of the controller. Okay, so we want to like design this controller in such a manner that it can improve the performance, steady state performance, and the transient performance, and the and the stability. So this is the error signal. Let me mark few points down. Okay, here at this point we're getting the error signal for like unity feedback. You can say this is the error signal, and how you want to define the error signal, that depends on the designer also. Like the controller, how you want to define the error signal, how you want to define the reference, all this depends on the who is designing the system. Okay, so yeah, so until now what we have been doing, we have been analyzing this block. Okay, we've been analyzing this block, that how is the stability, how is the time domain performance, all those things. Now we will analyze this block also to understand that what things we need to put in this block so that it can improve all these things. So sensor, we already know, it just senses the things. Okay, and like in block diagram, simple block diagram, if I want to convert this will be GC of S, which is the transfer function of the controller, and GP of S is the plant transfer function, and we have unity feedback system. So mostly we will work in unity feedback system only. So but before going into much depth in the controller, I want to give you a quick revision of the time domain parameters and the frequency domain parameters, because without those, understanding this controller part and compensator part is just worthless. So let's do a quick revision. So if you recall this graph, what is this graph? This graph is from the frequency response analysis, the first chapter, like frequency response of standard second order system. So here I have different plots, okay, for the gain versus the frequency plot, okay, and like as you can see, for zeta equals 0, I don't have a resonant frequency, like it goes to infinity, like at omega r, and for zeta less than 0.707 and greater than 0, my graph will look something like this. If you recall correctly, it will have a resonant peak of MR at resonant frequency omega r, which is equals to omega n into 1 minus 2 zeta square, where zeta has a condition. Zeta should be less than 0.707 and more than 0. And here this will be my plot for a system which has zeta greater than 0.707. And for critical damped also it is almost similar. Okay, I hope you're recalling things. Like you have to also revise things, right? You just cannot study new things and just forget the previous topics. You have to keep on revising things, keep on practicing questions along with it. Okay, so now what was the resonant frequency definition? The resonant frequency definition was that the frequency at which the amplitude of the response to a sinusoid input will be maximum. Basically what it does the amplification. We have studied in network theory also. Basically it is the amplification. Amplification. That is what resonance means. Like in network theory, in series resonance it was voltage amplification, and in parallel resonance it was current amplification, if you recall correctly. Okay, so that is what resonance means here also, that we give some sinusoid input, and at what frequency of that input my output amplitude will be response will be maximum. Okay, this was for zeta between this, and the formula was something like this. Okay, formula was something like this. Do remember, this is always for underdamped, only for underdamped. Only for underdamped. So like let's just write few relations here. If I see one thing, if I increase zeta, what will happen? This term will increase. Okay, let me write here. If I increase zeta, then this term will increase. Then what will happen to this term? This term is increasing, but this is reducing. Okay, so if I increase zeta, this term is increasing, but this term is reducing. Okay, so like how can you understand? So here if you see, like we have already plotted that in our graph plots, like in our previous chapters, that if I keep on increasing, sorry, not increasing, sorry, I meant to decrease zeta, because what you can observe here is that here my zeta is maximum where my peak is minimum. Okay, peak is minimum, and then I slowly go reducing zeta. Okay, my peak increases, then I go to 0, my peak further increases. Okay, so like as I'm moving this side, my zeta is reducing. Okay, I should write it like this. This will be much better to understand. Okay, just hold on a second. As my zeta is reducing, my peak is increasing. Like from the graph itself I can understand, as my zeta is increasing, my peak is increasing. Sorry, zeta is reducing, my peak is increasing. So zeta is going from here to here. Okay, from this end to this end. So as I can observe that my zeta, as zeta increases, my peak, sorry, as zeta reduces, my peak increases. Peak resonant frequency increases. Okay, here if my zeta reduces, so this is reducing, fine. What is happening to this? This is also reducing. Okay, and 1 minus this is increasing, but which one is like reducing at a higher rate? Okay, but I mean which one is more dominant? So here let's take an example. So we have 0.5 under root 1 minus 0.5 whole square. So this is almost 0.5 into under root 0.75. Okay, so now I am further reducing zeta. This is 0.25 into 1 minus 0.25 whole square. This will be into point, it will be almost 0.0625, so just 0.94, almost 1 itself. So like this one didn't change much. Okay, this one is almost similar if you find the value, but this one went to 0.25, this one halved. Okay, so this one reduced by huge amount, but this one didn't increase by much. So that's why this one is more dominant. Okay, that's why we tell like this, that our peak will increase, because this one is more dominant, and whatever happens to this will define the whole behavior of MR. So I can say that my MR, you just put few values down and you will see my MR is inversely proportional to zeta. Okay, like for like smaller values, I'm talking about for smaller values. Okay, for smaller values. Okay, so this is this. Now what about the cutoff frequency? Now like this was the next parameter. So this is the cutoff frequency, also known as the bandwidth also. This we can say as bandwidth also. Okay, sometimes we say this as bandwidth also. Also this is denoted like omega c also. So it is the half power frequency, or the frequency at which the magnitude response will be 1 by root 2 times of the DC response. So this is my DC response. Okay, the magnitude is KCL. In dBs it will be something else. Okay, 20 log KCL. Then if we subtract 3 dBs with it, the frequency at which the magnitude is that is the cutoff frequency, or you can say that is the bandwidth distance from the origin. Okay, and the formula is this. Like we derived it there. I won't go much further into this. We get formula something like this. Now one thing I can say is that if let's say my zeta reduces, what will happen? If my zeta reduces, okay, so zeta is reducing here, so overall this thing will increase, because this is negative sign. This is negative sign, so if this reduces, overall this thing will increase, and this reduces, overall this thing will also increase. So if zeta reduces, my omega c increases, or my bandwidth increases. Okay, so what I can say, bandwidth is inversely proportional to zeta. Okay, so my bandwidth is inversely proportional to zeta. So this is the relation that we found out. Now one thing I skipped over there during the explanation, that why do we choose this DC response? So if someone has already studied about bandwidth or things, they will tell you that we generally for low pass filter it is a DC response, but generally we choose the peak, the 3 dB down from the peak we choose as the bandwidth, but here we're choosing as the DC response, which is not the peak. So yeah, this depends on the designer what he chooses. Okay, but why we chose here the DC response is because, like here I've written down the question, that why we didn't choose the peak resonant at the as the reference for calculating cutoff frequency, because my peak resonant is itself some function of zeta. Okay, it is keep on changing, but my DC gain doesn't change. It is always KCL. It is always KCL, like not case of current law. It is K small, like subscript KCL. So it will, like my peak resonant will vary as zeta varies. Hence we choose DC gain as the reference, because if zeta itself varies, one thing is for sure, like obviously our cutoff frequency varies with zeta, that is fine. But if my peak resonant also varies with zeta, then that will also be difficult for us to calculate the this cutoff frequency. It will be very difficult for us to find the cutoff frequency. If my reference KCL is constant, it is not a function of zeta, then it is much easier for us to calculate this cutoff frequency. That's why we choose it like this. But yes, it depends on the designer. He can also choose the peak also. But the convention is to choose the DC gain. Okay, so yeah, this was one thing I wanted to mention clearly. Now, what about the cutoff rate? Now this one I skipped over there, like in that chapter in the second order standard frequency response of standard second order systems. It doesn't matter, like these things are just terminologies. Okay, so wherever rate comes up, whenever rate comes up, it is definitely some change in time, right, or change in something, differentiation of something. Okay, so here it is the slope of the log magnitude curve at the cutoff frequency. It is very defined that it is a slope of the log magnitude curve at the specifically at the cutoff frequency, So how can we write this in terms of mathematical terms? So cutoff rate will be equals to d of g d omega equals to omega c. So like this is the mathematical representation of this cutoff rate. So cutoff rate will be the slope of the magnitude curve, like simple Bode curve you can plot, slope at that point at the slope at the cutoff frequency. Okay, simple definition, nothing, not much. Okay, so yeah, these were the parameters for frequency response. Now let's come to the time domain. So let me write here. So these are the frequency domain parameters. Okay, I can't write. That is unfortunate. Let me write it in like. Write it in small here. So I can write this in the next. Sorry for wasting your time. I can write this in the next here. Here I can write, right? So yeah. Okay, so these are the frequency domain parameters. Now these are my time domain parameters. So like, let me write this. So these are the time domain parameters. So like let's go through them. First is the rise time. So if you recall correctly, it was the definition for a first order system was from 0 to 90%, and for second order system it is 0 to 100%. So here like how we derived it, we made like first time when it reaches 100%, right? So then this term we made it 0, if you recall from the time domain expression, the second order standard second order time domain expression. Okay, that we made 0, and from there we found our rise time. So this is very important. Okay, you have to remember this, very important, because through this we will compare many parameters. So then what was the peak time? What was the peak time? So peak time was the when it reaches the peaks, right? So when it will reach the first overshoot, then first undershoot, then again second overshoot, second undershoot, and the oscillation will die down, if you recall from here. So this was the standard graph of a standard second order random system. So this is here, I should write here that obviously all these parameters are defined for zeta between 0 to 1 random system. So zeta is between 0 to 1. Okay, so all these parameters are defined for this. Now here what do we see? Like the peak time. So peak time was this, like when we made this equal to pi, if you recall correctly how we derive it. So it was n pi by omega d. Now n, if n is odd, that is 1, 3, 5, then we will have a overshoot, as we can observe here. First overshoot, then the second overshoot, third overshoot, and the first overshoot is the maximum distance we get from the steady state value. And if n is even, then we will get undershoot. Okay, if it is below the steady state value, it is undershoot. It is over the steady state value, it is overshoot. So at n equals to, like, the very important point is that at n equals to 1 we get first peak, and at n equals to 2 there is a different color. We get the second peak. Okay, so these two are the things that we get. Now here, like, there is an overshoot, like the value of the overshoot. What is the value of the overshoot? You put at the standard equation like this, that t equals to this. Okay, and you will get your overshoot and your undershoot, and n like is varying 1, 3, like this. N will be odd here and n will be even here, and like the maximum peak overshoot will be what when n is equals to 1. So here if you check, like this is the graph, and like the error band is within 90%, if you recall correctly, like the steady state error band, like when it reaches within the 90% error band, then we say that yeah, it has settled. And the time period, the time that it took to settle is known as the t settling time. Here, like, it is also equals to the 4 upon zeta omega n, if you remember correctly. Now what do you want to derive here? What is the t naught? T naught is oscillation, like time period of one oscillation. So this is equals to time period of one oscillation. Okay, so this is what my t naught is. Now one oscillation, like here, what do you mean by one oscillation? Like the oscillation starts from here and again ends at the steady state point, like, and then again another oscillation starts, and these have same time period. The time period will be same, but the magnitude of the oscillation, like the upper and lower bounds, the overshoot and the undershoot, will reduce further. So they have reduced, but the time period is same. So that is for one time period of oscillation. Now if I want to find how many oscillations, number of oscillations will occur before it settles, before my time, like this output response settles, that will be equals to n naught, the number of oscillations number of oscillations before settling. Okay, number of oscillations before settling. So this is the number of oscillations before it settles. So it will be equals to total time upon the time taken for each oscillation, t set by t naught. Okay, so these all these things I have already explained in detail. Just quickly revising you. Let's just keep over to next thing. So what is MPO? MPO is the maximum peak overshoot. When put like n equals to 1 in the overshoot formula, and you have to subtract with a steady state value, and your maximum peak overshoot will come like this. Now what is interesting here is that if you reduce your zeta, what will happen? Sorry for that sound. If you reduce your zeta, then this will increase, okay, and this will reduce. Now if this reduces and this increases, overall this thing reduces. So if this is reducing, then what is happening? Your MPO is increasing. Like there is a negative sign over here, so your MPO will increase. MPO will increase. So if MPO increases, what does that means? MPO increase means that your maximum peak overshoot and zeta are inversely proportional to each other. Just same relation as the maximum resonant peak. So I told you, right, they have few similarities between them, the time domain parameters and the frequency domain parameters. So MPO and the zeta are inversely proportional to each other. And what about my, like I told you, what about my T rise? So if zeta is increasing over here, okay, zeta is increasing over here, then what is happening? Then my omega d is equals to omega n. I'm assuming my resonant natural frequency is constant. So this will increase. Okay, so this is increasing. Now if this is increasing, overall this will reduce. So overall if this reduces, then this omega d is reducing. And what about the numerator? What is theta? Like my zeta is equals to cos theta. So if zeta increases, cos theta will reduce. Like cos theta will increase, but theta will reduce. So if theta reduces, this overall thing will increase again. So pi minus theta will again increase. So what am I observing? My zeta is directly proportional with the rise time. So I can write here my zeta and rise time are directly proportional to each other. Now these are very important things to keep in mind. Now one thing you might say, sir, if I try to reduce zeta, then we won't be able to tell. Why? Because if I try to reduce zeta, then this will I reduce zeta, so hold on a second. Sorry, this will reduce. Sorry, this will reduce. If I reduce zeta, then this thing overall will increase, and if I reduce zeta, then this one will increase, this one will also decrease. Okay, but this one is increasing and this one is decreasing. Yeah, then also you can say the same thing, that your rise time is reducing if I decrease zeta, because this one overall will reduce and this one overall will also increase. Okay, so yeah, you can like understand like that way also. So these are the few important relations that you need to keep in mind. Also the delay time, we don't care about delay time that much, but still, as I wanted to tell you, like it was from 0 to 50% of y of infinity. We don't remember this in this chapter. Now settling time. What was the settling time? For 2% error band, it was simply 4 tau, and for 5% error band, it was simply 3 tau. Now for underdamped systems, it is 4 by zeta omega n, and for overdamped systems, it is 3 by zeta omega n. Like simply 4 tau and 3 tau, and tau is zeta omega n. Now this one you remember simply the real part of the pole of the underdamped system. Now for overdamped, it is, you might say this is a very big formula. How do you remember this? No need to remember this. Now you know 4 tau, right? You know 4 tau, 2% error band. That you need to remember. And for this, just remember that for overdamped, whichever pole is more nearer to the origin, the inverse of that one is time constant. So no need to remember this. No need to remember pole, because it will have two poles. One will be dominant and other one will be farther away from the origin. The magnitude of that one, obviously, because it is in the negative direction, equals to 1 upon tau. Okay, equals to 1 upon tau. So yeah, this only you remember this, and from here you find the tau and you just do 4 tau or 3 tau according to the error band. So don't remember this. Now these were about the settling time. So here, like as you can see, settling time is also inversely proportional to the zeta. Okay, my settling time, T settling, I'm talking about underdamped systems, is inversely proportional to the zeta if I assume that my omega n is constant. Okay, so like what things we know until now, like settling time we know. Okay, and what about my other things? So peak resonant, we know it is inversely proportional to the zeta. Bandwidth is inversely proportional to the zeta. Peak resonance is inversely proportional to the zeta. Bandwidth is inversely proportional to the zeta. Okay, let me write these things down. MR is inversely proportional to the zeta. Bandwidth is inversely proportional to the zeta. Okay, and what were the other things? Okay, nothing else was there, I think. Yeah, nothing else was there. And now coming to the time domain parameters. Here my T rise is directly proportional to the zeta. T rise is directly proportional to the zeta. So yeah, like what we will do is compare this bandwidth and the T rise actually. So okay, and my like MP, maximum peak overshoot, is inversely proportional to zeta, just similar to the resonant peak. MP inversely proportional to zeta. Okay, so these are the things, and settling time I've already written. So like we will compare this two things. Like we are concerned with bandwidth, is that if my bandwidth is very high, that means it will take lower time to reach like the rise time, right? Rise time will be low, hence it will take lower time to initially getting to that initial, like the steady state value, initially getting to the steady state value. That is what rise time means. So mainly we're concerned with this bandwidth and the rise time. So like we'll try to relate these two. So like what does this mean? If my bandwidth is very high, if bandwidth is very high, then system is very fast. System system is very fast. Also, as my rise time is very low, T rise will be low. Okay, so my rise time will be very low as I got faster transient response. So yeah, these are very important actually to understand. Like, yeah, this like bandwidth represents the speed of the system. This also you will learn in analog electronics, I hope. So yeah, higher bandwidth means higher transient response, and it will reach like try to reach the steady state faster. Okay, so like rise time will be lower. It will take less time to reach the steady state value for the first time. Okay, so yeah, now why are we understanding all these things? Why are you like studying all these things? We want to exactly do this, make our system more faster, make our system more stable. How we do that? Basically, okay, so we can improve bandwidth, TR, all this by doing what? By changing zeta or some other parameters. Like I'm mainly talking about zeta here. Changing zeta. And how we change the zeta? How can we change the zeta? We can change the zeta just by simply changing our pole locations of the system. So changing pole locations. Now if we change the pole locations, then our zeta will change. So this is the main point I want to come to. We have to change our pole locations of the CLTF, closed loop transfer function, because zeta is defined for closed loop transfer function. Okay, so let's say I want to reduce my rise time or increase my bandwidth. I have to reduce my zeta. So how do I reduce the zeta? So initially, let's say my poles were here. On random system only, P1. Okay, so poles were here. Now I want to increase my bandwidth. How do I increase my bandwidth? By reducing the zeta. Okay, and increase my rise time. Now if I want to reduce zeta, then obviously let's say that omega n is constant. We are in this circle. Okay, let me, okay, I won't be able to draw a perfect circle. I will try to. Okay, please excuse me if I won't be able to. Okay, I will just move the pole locations then. Yeah, now like the omega n is constant because it is in a circle. I just want to increase my zeta I just want to reduce my zeta to increase the bandwidth. How do you do that? So this is what? This is zeta omega n, if you recall correctly. This is zeta omega n. Now if this is zeta omega n, what does this mean? This means that like omega n is fixed. If I make this more nearer to the origin, my zeta will reduce. So now if I shift the pole locations here, okay, like still it is under the amp system. Let's name this as zeta 1 omega 1, and let's name this as zeta 2 omega n2. Okay, so if I shift this pole locations, what will happen? If I shift this pole locations, this is P2. Okay, then obviously like zeta will reduce. So that is what we're doing. We're shifting poles. Okay, P from P1 to P2. If you move here, my zeta will reduce, my bandwidth will increase, my rise time will reduce. Okay, all these things will happen. So obviously that is the main motto. That is the main motto of this like chapter, to design those controllers in such a way that it can shift my closed loop poles. Okay, how do we do that? Like we have already studied this, that I told in the time response chapter. If we somehow added some poles in the OLTF, some zeros in the OLTF, then what does it affect in the overall system? So I have maybe I have forgotten to mention there that we are adding, like there we are adding the poles to the OLTF. The poles to the OLTF. What happens if we add poles to the OLTF, not to the CLTF, to the OLTF? Okay, what happens to the closed loop poles if I add poles to the OLTF? Also we'll study what happens if we add poles to the CLTF also. The difference we will also study. So first, the effect in closed loop poles by adding poles to the OLTF. So by adding poles to the open loop transfer function, the root locus shifts to the right of the S-plane. Like we have already studied this in time to some. I won't go much depth into this. It makes the system less stable and response becomes slower. How we will understand? So here initially I had, let's say, like parameter, system parameter k by s plus 1 first order system. This is the OLTF. This is the OLTF. This is the initial OLTF I had. Now what happened? I added one pole further away from the origin, like further from this plus 1. Then again I added one pole further away from this origin. Now let's plot the root locus for this. Like this is the system. Okay. Now what do we get from the root locus? Initially when like this g of s was like this, then the root locus was like this. It can never be unstable. It will always be stable. Whatever the value of k, it will always be stable. So for all values of k, it will always be stable. Okay, so this is the first thing. Now what is happening next? If I further add a pole, I'm observing still it is stable, but my like parameter is changing here. It is again becoming like a critical damp because it is second order system. It can be damping comes into factor here. So still stable, but damping comes into factor. Okay, now what is next? Next is if I add a third pole. Now if I add a third pole, we can see that it is not stable for all values of k. For few values of k, it is going, the poles are shifting. Poles of the CLTF. What are this? These are the poles of the CLTF. That is what the root locus defines. So the poles of the CLTF are going on the right hand side of the S-plane. They are going on the right hand side of the S-plane. So here this is not stable for all values of k. So we learned about the stability. If you keep on adding poles to the OLTF, so we have to take care of this. Like whenever we are adding some poles to the OLTF, the system may become unstable. Like we have to take care of this when we are designing the controller. Okay, because in controller mainly we'll add poles and zeros to the OLTF. Obviously we can't change it to the CLTF. Like we are adding our controller was in, where it was in the forward path gain. It was in here before this plant. Okay, before this plant. Okay, that is why I wanted to like explain you this. Now let's go into the second parameter, effect in performance parameters by adding poles to the OLTF. Now we understood that what will happen to the poles itself, what will happen to the closed loop poles itself, but we couldn't understand the performance parameter, like the frequency domain parameters and the time response parameters, frequency response parameters and the time response parameters, because what was happening, we were varying our k also. Okay, system parameter k also, but now we will simply fix our k and we'll see the effect in effect in adding poles and fixing the k and effect in the performance parameter while fixing the value k. Only then we can simply analyze this. So here my k will be fixed else we won't be able to analyze this, because if k is also varying and also we're adding system parameters, then we won't be able to compare apples for apples, simply the performance parameters. We want to see how the zeta varies, how the MPO varies, all those things. So here k is fixed. So let g of s be a simple OLTF, like 4 upon second order OLTF, so that we can compare the time domain parameters. Without second order, the concept of damping won't come. B equals to s plus 4. Okay, so now here in this case our k is 4. Okay, the k is fixed, k is 4. I will write g of s like this, 1 and k equals to 4 fixed, so that we can compare after adding the poles. Okay, so now what is the characteristic equation of this one? So the characteristic equation is s square plus 4s plus 4 equals to 0. Okay, this is the characteristic equation. So here what is my omega n? Omega n square is 4, so omega n will be 2. Okay, so omega n will be 2 radian per second. Okay, so this is my omega n. So what is my zeta in this case? So my zeta is 2 zeta omega n is 4 equals to 2 by 4, which is 0.5. So zeta is 0.5. Okay, so sorry, this is 4 upon 2 times 2, which is 1. So zeta is 1 in this case. So right now my zeta is 1. Let's see what happens after I add a pole. So if you observe, like if you draw the root locus of this one, how it will look. So like now, like how I draw the root locus is varying the k. Okay, and at 4, how are the behavior of the roots, I can also observe from the root locus also. So just hold on a second, let me check if everything is recording. Yeah, everything is recording, fine. Yeah, so just briefly drawing the root locus. So here where are my open loop poles? They are at s equals to 0 and s equals to 4. Simply how will the root locus go if I am varying the k? So they will move like this, and somewhere in between they will break away. Okay, this is equals to -4 and 4. So as I am observing that like it is underdamped in this case, so obviously my roots will somewhere lie around here. Okay, and like the real part will be zeta omega n. So it is 2. Like what is zeta omega n? Zeta omega n is 2 itself. So obviously like the wherever it is underdamped, the real part will be 2 itself. Okay, so yeah, like somewhere around here my k will be 4. Okay, in these regions my k will be equal to 4, and I'm lying in this region. Okay, so you can understand from the root locus also like how will my behavior be. Now this is my root locus. I have already told you what happens if I add further poles, okay, to the OLTF. What happens to the root locus? It shifts to the right. Okay, right. So now let us add a pole on s equals to 10. Okay, s equals to -10. Let me add a pole and let's see what is the effect in the time domain parameters. We know what happens to the stability. Obviously, it tends to become more unstable. Now let's add a pole. This is 0. Add a pole at s equals to -10. Let's see how does it affect the time domain parameters here. So what happens to the OLTF? So the OLTF becomes something like this, like my new, let's name this as G dash of S. It is 4 will still remain because K value is 4 still, divided by S into S plus 4 into S plus 10. Okay, so this is my OLTF basically. So now can we further find this one out? So like if we write the characteristic equation of this one, what will it become? It will become S into S square plus 14S plus 40 plus 4 equals to 0. Okay, so this becomes S cube plus 14S square plus 40S plus 4 equals to 0. Okay, so here like I have already used a calculator, like online calculator, else we won't be able to analyze this. So if we use the online calculator to find the roots of this one, so my first root of this one will be minus 10.08. okay, minus 10.08. My second root will be minus 3.83, and my third root will be minus 0.1. so what is happening, like previously my all of my poles were around here, but few poles were going more closer to the origin, okay. This pole is moving more closer to the origin, which was expected. Like I was telling that if my pole, like if I add a pole to the OLTF, then what will happen is that my system will tend to become more unstable. That's why moving more closer to the origin. This is one thing. Now what is the other thing? What we are observing is this root is very far away, okay, far away from the origin, very less dominant, hence we can ignore this one. Okay, we can simply ignore this one. So if you simply ignore this one, then we have only these two poles. We have, like, these are the dominant poles which are near to the origin. This is much far away from these two poles, right? So I can ignore this one because this will not affect the transient state, transient response. So what do I see? I have two poles and which are not equal to each other and which are negative. That means my system is overdamped. System became overdamped. Okay, so my system became overdamped. So if my system became overdamped, what does that mean? My zeta has increased, because previously it was underdamped. Previously my system was underdamped, now it became overdamped. Okay, so previously it was here, as we can see, like where was I? Yeah, zeta was 1 previously, like it was critical damp. Okay, but now it has become overdamped. So from critically damped to overdamped, that means my zeta has increased. Okay, so this is the first conclusion that we draw from this. Now let's say we added a pole very far away from the origin, right? We added a pole at s equals to minus 10, which is very far away from the origin. Now let's say we want to add a pole a bit nearer to the origin. Let's add a pole more nearer to the origin. Okay, so let's add a pole SP at -4. Okay, let's add this. So what will be the effect of this? So now what does my G double dash become? So let's name this as G zeta increases, so I can compare that my zeta dash is greater than zeta double dash. Okay, I'm not talking about the omega n, because what we have to do, we have to simply divide this equation by this, then from there we can find the omega n and zeta also exact values, but I'm not writing the exact values right now, not writing those. Okay, so now my G triple dash, what does my G triple dash become? G triple dash simply becomes 4 into S. Okay, so why should I add the pole here? S into, okay, no, sorry, actually S at S equals to 4 we already have a pole, so I should add at S equals to -2, else it will become simply square. We can do that also, but let's add it more near to the origin. S plus 4 into S plus 2. Okay, we are adding more near to the origin. Now what will happen is that, let's write the characteristic equation. S square plus 6S plus 8 equals to plus 4 equals to 0. So S cube plus 6x S square plus 8s plus 4 equals to 0. So here, like, what will be the roots of this one? Again, if I just put it in the calculator, it will be simply SP1 will be somewhere around -4.1, which will be again further away. P2 will be around 0.5 plus, oh sorry, 0.8 plus 0.5 iota, okay, complex number. And SP3 will be, like, the real part will be same, it will simply complex conjugate. Okay, as my coefficient are real, hence I will get simply complex conjugate poles. So what does complex conjugate poles say here? First thing is, this one, like, the real part of this is -0.8 and this is -4.4. So this one is much nearer to the origin than this, and this is also like 4 times lower of this. Okay, so we can ignore this one from the dominant pole concept. So dominant pole concept we can ignore. Okay, so very far. Far away from the origin. So this is 0.8 and this is 0.5. Okay, so now, like, we can ignore this. Now what does complex conjugate poles mean? We have a underdamped system. Now if you have a underdamped system, what does that mean? That means that I will have zeta and omega n, obviously, but my zeta will be less than 1. My zeta will be less than 1 definitely. Okay, so let us just calculate the zeta and omega n. Okay, like, system is underdamped. So my zeta reduces. Okay, so obviously what I can say is zeta will lie around here. Let me write this in different pen. Zeta will lie around here. My zeta dash double dash will lie around. Okay, this was this single dash. Okay, sorry, this was single dash actually. This will be double dash. Yeah, so this is single dash, and like zeta double dash will lie around here. because uh, because like they will because like it is under damped, so obviously it will be less than 1. It is over damped, it will be more than 1. Here this is between. You can calculate it. You can calculate the zeta and omega and zeta. You will see how they are varying. Okay, we don't have time, so I won't do this much here. Okay, but just keep in mind one thing. If zeta is like zeta is not is greater than 0.707, then no concept of bandwidth will come up, right? No concept of bandwidth will come up. So what is happening is, if we add pole more closer to the origin, what is happening is my zeta is reducing. So adding, like, you can calculate the values. I'm not calculating in them, that's up to you. Adding poles more closer to origin, zeta reduces. Okay, if you add it further away, obviously zeta will be higher than this. Okay, so yeah, this is the basically crux and conclusion of this. Omega n doesn't vary that much, but zeta reduces. So if zeta reduces, what will happen? My bandwidth will increase. Okay, so like I have the different plots here also. Like at first, like it was critical damp. Okay, it was critical damp. Now we added a pole very further away from the origin. If we added a pole very further away from the origin, it become over damped. Now if we add a pole very nearer to the origin, then it will become under damped, and like zeta will keep on reducing. So here, further away from the origin, this is and this is nearer to the origin. Okay, so this is near to the origin. So here, like this is a comparison between each of them. Like you can compare the peak, resonance, all those things, right? So like if our zeta reduces, then what happens? The damping becomes lesser. If zeta increases, damping becomes more. So if zeta reduces, the maximum peak will reduces. If zeta increases, maximum peak will reduce, or which is the rise time will reduce if zeta reduces. Directly proportional, as you can see, right? It has the lowest rise time, reaches the steady state value for the first time in much lesser time than these other plots. So what are the things we observe from this cases? So like as I said, right? So bandwidth will increase if zeta reduces. So I can say that my initial bandwidth, like obviously it was critical damp, so I can't talk about bandwidth, but let's say a ballpark number. Let's say all the three systems were under damped still after adding poles. What will happen if I add pole further away from the origin? Then my bandwidth will reduce. So my bandwidth will come here. Okay, and if I add pole more nearer to the origin, then my bandwidth will increase. And as I said, right, if bandwidth increases, the rise time will reduce. So rise time will just follow the opposite rule. So my rise time, as I can say, that my rise time TR will be just opposite. So here what will happen? So like sorry, this is double dash and this is dash. So obviously, like if I add more nearer to the origin, then my rise time will reduce, as we saw from here, right? As we saw from here, the system becomes more and more, zeta reduces further, and hence it reaches, like its first time it reaches its steady state value at a much faster rate. That's why rise time reduces. And obviously if rise time reduces, bandwidth will increase, and vice versa. Okay, so these are the things that I wanted to compare. Obviously, what will happen to my peak overshoot? My peak overshoot will increase. Okay, so initially if I had some MP, let me write this in same color only. If I have some MP, then if I add pole much nearer to the origin, my peak overshoot will increase. Okay, and if I add pole much further away from the origin, then my peak overshoot will reduce. Okay, so this will be double dash, and this will be single dash. Okay, so this will be just similar to the bandwidth only, and like the MR is also, MR will be also same only, because MR and MP are almost same, because they are like inversely proportional to the zeta. All these three things, just T rise is directly proportional to the zeta. So if my omega n is, I assume that omega n is almost constant. MR double dash and M1 dash. Okay, so yeah, like we can see the relations if I add pole further away from the origin or pole near to the origin. All these are conclusions that I wanted to note here. So now what we'll do is we'll add poles to the CLTF, and let's check what happens to that. So what will be the effect in closed loop poles by adding poles to the CLTF? Now, can we change anything when we add closed loop poles? Can we do anything? Obviously, adding closed loop poles is in itself is very difficult. But even if we are able to add closed loop poles, then what will happen? So first, I will analyze this in the time constant format. So here everything is in time constant format. So like I'm adding poles in the time constant format. So here, let's say initially my transfer function, now it is not my OLTF, it is my CLTF. My transfer function is S4 by S square plus 4S plus 4 into 1 plus S tau. This is added in the time constant format. Okay, 1 plus S tau. So now what will happen? Now one thing we observe is this is already a critically damped system. This is already a critically damped system. Now if I add another pole to it, what will happen? Can I ever make it underdamped? Can I ever make it underdamped? The simple answer will be no. Because just understand one thing, if I add a pole very far away from the origin, okay, very far away from this S equals to -2, if I add a pole very far away, it is non-dominant, this one will be dominant, and my system will remain critically damped. Point 1, my zeta won't change, my omega n won't change. Now if I add very nearer to the origin, if I add a pole very nearer to the origin, then what will happen? Then my system will become overdamped, because one pole I can ignore and another pole is very near to the origin. Okay, it will act like a first order system only. Other poles are very far away. Okay, with respect to this, dominant pole concept will come up, and I will only assume this pole, and other pole I can ignore. Okay, so it will be like a overdamped. At max, I can make it a overdamped system from critical damp. I won't be able to make it a underdamped system. Okay, so from critically damped we can make it a overdamped system. Okay, overdamped, let me write it fully, overdamped system we won't be able to make it undamped. Okay, this is very important. Like you can understand from here as well that what is this is s plus 2 whole square into s tau plus 1. Now what we can do, we can simply use the partial fraction method. So simply use the partial fraction method. What we'll get, we'll get one term a into s plus 2 whole square plus b by s plus 2 plus c by s tau plus 1. Okay, so we'll get three terms, and like this will give one exponential. Now if this is much nearer to the origin, this will dominate. If these are much nearer than this one I can ignore. Okay, and still like this, what is this? The denominator will be s plus 2 whole square only. Okay, that means it will be a critical time only. I can ignore this one. Else if it is much nearer to this, the denominator will be this, and this ones I can ignore. So this will be like a first order system. Okay, so yeah, basically, so if I add pole much near to the origin, my zeta is increasing. That I can say. If I add pole much near to the origin, my zeta is increasing. Okay, so that is one thing. Now so here my zeta will increase. Okay, zeta will increase. Now for underdamped, what will happen? If I had a underdamped system, it will go more towards overdamped. So initially, let's say initially I had a underdamped system. Okay, now initially if I had a underdamped system, what does that mean? If initially I have an underdamped system, then that means that if I now add a pole, what will happen? Much nearer to the origin, that will dominate. Again, that will become overdamped. Okay, and if I add much further away from the origin, it will be still remain underdamped. So like if I add nearer to the pole, my zeta increases. Okay, so nearer to the origin, zeta increases. Okay, as system becomes overdamped. Okay, so this is the case. So like the simple thing, closed loop poles, if you add more near to the origin, zeta will increase, else zeta will reduce if you add further away from the origin. Okay, the simple thing. Okay, this is the conclusion from this. Now effect of closed loop poles by adding open loop zeros, by adding zeros to voltage. Like we have already done this in the time response chapter. So by adding zeros to the open loop transfer function, the roots shift to the left of the S plane. So like it becomes relatively more stable if we add open loop zeros to the root locus. Makes the system more stable, response become faster. Like this is conditional, obviously. Like how does the response become faster, we'll understand. Okay, here what was the response? Here what we are observing is that my T rise was lesser. Okay, but my settling time will increase. So like here, as we observe, right, my T rise was reducing, rise time was reducing, but my settling time will increase because settling time is inversely proportional to the zeta. So have I done it? Have I written it down here? Yeah, my settling time is inversely proportional to zeta. So my settling time will increase. So obviously it will take more time to settle. So here I can write another parameter that it will take more time to settle. So I can write the frequency domain parameters here. Like, let me just copy the parameters. Settling time will increase, obviously. Sorry, this yeah, this will be double dash. This will be, sorry, this will be up here on the right hand side. Okay, so my settling time will here increase. So this will reduce and this will increase. Okay, so like but in for a 0 the response becomes much faster. Settling time reduces there. So like we will observe that. So here, so what happens? Let's say I add a 0 over here. Like this was my transfer function, right? S plus 1 at the end after adding the poles. Now if I add a 0, so initially this is the root locus. If I not add a 0. Now if I add a 0, my root locus becomes this. Now again, right, for all values of k, this is stable. So this becomes relatively more stable. So relatively more stable. Okay, so this is the first thing. Now here, like just this we want to understand that yeah, it becomes relatively more stable. Now what happens to the performance parameters? Now we have to obviously fix the value of k. So k is fixed again, k fix, else we won't be able to analyze the performance parameters. So here, like initially, let's say my system was like this, 4 upon s into s plus 2. Okay, now I add a 0 much further away from the origin. So if I add a 0 much further away from the origin, s1 plus s by 10. This is still here, s into s plus 2. So for this, what was my omega n and zeta? Omega n was equals to 2, my zeta was equals to 1. Okay, sorry, zeta was equals to 0.5. Okay, for this zeta is 0.5. So this case, like, just hold on a second. This is plus. Yeah, this was okay. This was this. Yeah, everything is fine. Yeah, zeta is more. So it's critical time. Fine. I was just checking one thing. So for this case, right, like I've chosen the zeta different. Okay, that's why I got confused because previously zeta was 1. So this case I've chosen the zeta different. This case I'm choosing the zeta as 0.5, just to make you understand one thing. So like this, to make the system underdamped so that we can understand the differences. So here when zeta is 0.5, you can easily analyze this. Like just put s plus 4 and you will easily analyze this. Like this will be s square plus 2s plus 4, and from there you will find zeta equals to 0.5. Now what about this? Now this is the OLTF, right? This is the OLTF. So what will happen to the OLTF? Like my CLTF will become 4 upon s square plus, instead of 2s it will become 2.4s plus 4 plus 0.4 times s. Like this term is also there. This term is also there, right? This term is also there. So we can't just simply ignore this one. This one will also come in action. S square plus 2.4s plus 4. Okay, so yeah, this is this. Now what will be the response of this one? Like, so this one is simple, this one is very simple. What will happen to this? So for this, my characteristic equation is 2s plus 4. My omega n is still 2, but my zeta is 2.4. So my zeta becomes what? 0.6. So I can see that my zeta is increasing here. So my zeta is increasing here. So if my zeta is increasing, what does that mean? That means my rise time will increase, my MP, MR bandwidth will reduce. But what we have to keep in mind over here, like as it is less than 0.707, obviously these parameters will come into factor. MR and this will come into factor because my zeta is, always keep this in mind, right? This you have to keep this in mind, that less than 0.707. Okay, so what other thing? Other thing is that my zeta is increasing, but we have this term also. We can't simply forget this term. So what is this term? This term is like S is there and everything else is almost same. There's a constant different. So this is the differentiation of this response. The differentiation of this response. Now, if this coefficient is very low, then we can neglect this. So what I am doing currently, as I have added a pole much further away, I can see the coefficient is very low, 0.4. 0.4 times this response is lower compared to this. So this is still dominating. This response is still dominating. This is, what does this S means? S means the differentiation. We have already done this in the basics. So as like I'm doing this, I'm ignoring this now. Next example, I will take this. So as this is 0.4, very low, ignoring this. I'm ignoring this. Okay, so yeah, this is this case. Now let's add another 0 basically. So let's add another 0 which is much nearer to the origin compared to this. Now I add a 0 here. S equals to sz equals to minus 10. Okay, I added a 0, sz equals to minus 10. Let's add a 0 much nearer to the origin. So if I add a 0 much nearer to the origin, what does it become? So here this is the case 1. Okay, case 1, this is the case. Let's name this as case 2, case 1 and case 3. Let's say I add a 0 at s equals to minus 3. What happens then? So, yeah, s equals to minus 3. If I add, then my equation, so this is g of s. Forgot to write all this, sorry. G dash of s. So now my g double dash of s, what will it become? It is s by 3 plus 1 divided by s into s plus 4. So this is s plus 2. And we have also a 4 here. Okay, so now what does my CLTF become? So my transfer function, it becomes like there will be 4 here. This will be s square plus this is 1.33 plus 2, that is 3.33 s plus 2. Sorry, this will be plus 4. Plus 4 by 3s s plus 3.33s plus 4. Okay, this time this is greater than 1. Okay, this time this is greater than 1, and obviously this will affect somewhat. How it will affect, we'll understand. So again, like my omega n is fixed, omega n isn't changing, omega n is still 2, but my zeta, what is happened to my zeta? Zeta, like 2 zeta omega n equals to, you can say this as 10 by 3 you can say this as. So this will be 10 to 5 by 3 5 by 3 5 by 6 5 by 6. So this is almost equals to 1.667 into 5, which is 0.833 something. Okay, 0.833 something. So zeta is still this. So what is happening to zeta? So here, if you observe, it was 0.6. Again, if I add it more nearer to the origin, the zeta increases. But we have to take care of this equation also. So how to take care of this equation? So like I've drawn few things here. I've already drawn the response. So let's say this is a simple second order standard response where my zeta is 0.83. Okay, there is no 0 over here, there is no S term over here. Simple standard second order response where my zeta is 0.83. Okay, so my zeta is 0.83. Now what happens? Now what was that response? That response is simply the differentiation. A multiplication S is simply differentiation in time domain. This is in time domain. So this is the differentiation. Okay, simple differentiation of this. So here what is happening? My slope is positive here. So obviously it will be positive. Now suddenly what happens? It reaches a maxima. So my the differentiation of this will be 0. It is a local maxima. So differentiation of this will be 0. Then what happens? It is reducing. So my slope is negative. Negative. So again slope becomes negative, and then suddenly it reaches like minima. So local minima. Again my slope will be 0 around here. So this will go on like this. Simply it's the differentiation of this. This orange curve is the differentiation of this Euler curve. So this Euler curve is simply, the transfer function is this. Like let me name this as C dash of S is simply like I will name this as something else. I should name this as, so it is simply the response of 1 over S, like unit step, into simple 4 upon S square plus 3 okay, let me write this in small letters, else this will be very hectic. 4 upon S square plus 3.33 S plus 4. Okay, now what is this? This is, let's name this as C double dash of S. This is simply the differentiation of that. So it is R of S, which is 1 by S, like 1 by S is the unit step, right? R of S into S into 4 by 3 upon S square plus 3.33 S plus 4. Okay, so yeah, this is the differentiation of that one. Okay, so 1 by S is simply the Laplace of unit step. So this is like C of S equals to R of S times a transfer function. That is what I'm writing over here. Okay, so further specify this. So what will be the actual response? The actual response will be the summation of these two. So initially both of them are positive. And increasing over here. So obviously until this part, okay, both of them will increase. So here it will be something, okay, my drawing will be really bad, so please like forgive me. So this will increase, okay, and suddenly like still it will increase, because still this is positive, this is also positive, but here this is reducing, and this is like at this stage this is negative. So it will be something like this. Then after reaching the maxima here, it is negative, so this will further reduce this. Okay, now one thing will be important. If my 0 is dominant, if 0 is very dominant, then obviously my rise time will reduce, because this will reach its steady state point much faster. It will reach its steady state, first time it will reach its steady state point much faster. So this is the case where my 0 is very dominant. This is the first case, right? This is the first case. Sorry, the second case. So where my 0 is very dominant. So what is happening to the first case? In my first case, my curve will be something like this, because the magnitude is much reduced. Okay, so it will not increase it very further. It will be same only. Obviously my T rise will increase, but it will not increase it very further. Also, it may so happen that it may decrease also. Okay, so here if my 0 is not very dominant, obviously it will be same only. It will be almost similar to this curve only. Now if my 0 is dominant, what is happening? If my 0 is dominant, it is increasing my reducing my rise time, because reaching the, so this is, let's name this as 4, reaching the steady state value for the first time at a much faster rate. So here my rise time is reducing. Okay, all this we have studied. Now let's study the effect of closed loop poles by adding the zeros basically. Where was it? So yeah, effect of closed loop poles by adding zeros to CLTF. Now if we add the zeros to the CLTF, what will happen? So initially, let's say my transfer function is something like this: 4 upon s square plus 2s plus 4. Now if I add a closed loop 0, which is let's name this as s upon omega z plus 1. Okay, s square. Like, why am I adding in time constant format? So that it won't affect the DC gain of my system in the closed loop format. That's why. (2s plus 4). Now this is 2s plus 4. Now, like, what will happen if I break this one down? Like into two components, right? So summation of two components, t dash of s this one of the component will be same only, s square plus 2s plus 4. So obviously my zeta I can't change, but it will change. Why? Due to this 0. It will depend on the dominance of the 0. S by omega z s square plus 2s plus 4. Okay, so this is the thing. So like, what will happen? So let me just draw the response of this. Okay, let me just draw the response. Like, I'm drawing the step response of only when my transfer function is this. So how will the response look? Again, what is the zeta here? Zeta here is what? 0.5, and omega n is 2. Okay, so if I just simply draw the step response, it is underdamped, so it will be something like this. Okay, so now again, what will be the differentiation of this? So if I do the difference again, it will be like a similar case only, previous case only. So if my omega z is very high, so let me just draw two things. Let me first draw two things, then I will explain you. here these, let me just mark the maxima and the minima points. Okay, so this here it is positive, here it is negative, here it is positive, here it is negative and positive, like this. And let me mark another point. Here it is positive, here it is negative, positive, negative and positive. So what is happening is that like this orange curve is for omega z2, which is greater than this blue curve, which is omega z1. So omega, sorry, it will be other way around. Omega z2 is lower than this omega z1. Okay, so omega z1 is higher, so it is further away from the origin. So this means this is nearer to the origin. Okay, so this is further away from the origin, this is nearer to the origin. So like if the magnitude is much higher, so obviously my TR will reduce. Now if my magnitude is again lower, my TR will again it will increase instead of this. So here the combination of these two, it will rise up much faster, and combination of these two, it will rise up slower. So for this case, for comparison of this case, what I can say is that TR what do you say, TR1 yeah, in the second case TR2 will be much lesser than TR1. Okay, so TR2 will be much lesser than TR1. So like you can see, like for this case, like if the magnitude is much lower, it will be almost like this only, and if the magnitude is much higher, we are adding these two up, so my TR will reduce, because the first time it will reach its steady state will be much faster. Okay, as this is getting added. Okay, so yeah, from here we can understand TR is reducing as omega z is increasing, TR is reducing. So as we are adding a0 further away from the origin, sorry as we are adding much nearer to the origin, my TR is reducing. So adding 0, sorry. Now does this have a negative effect? Yes, this does have a negative effect. Adding 0 nearer rise time reduces. Okay, other things will obviously, if both of them are underdamped, then all these things will come into picture. My MP will increase, obviously MR will increase, and bandwidth will increase. Okay, so these things will increase. Now what will happen is that if, let's say, if I add a right hand 0, I've already explained this in like first few chapters, basic chapter, that if I add a right hand 0, if we add a right hand 0, what will happen? What will happen if I add a right hand 0? If I add a right hand 0, will this be same? No. What will happen? This will just the opposite. This will just be the opposite. Okay, so let me just copy this. I will just tell you what will happen if I add right hand 0. We have already done this. We have already done this once. So now my omega z will be what? My omega z will be negative. Okay, omega z will be negative. That means yes, there will be differentiation of this, but in the opposite direction. So as here the slope is positive, my output will be negative, because negative sign is there, because omega z is negative this time. Omega z is negative this time. So let me just mark this point. So now what we see is, initially this is much higher, this is increasing but not at a very fast rate, this is much higher than this, the magnitude. So my resultant will be negative initially, okay, then obviously at some point it will become positive, then again it will be like this, okay. I'm not drawing it exactly, but it will be like this, the summation, okay, resultant. So what is happening? Obviously my rise time is increasing, that is true, but also initially starting from negative direction, okay, starting from negative direction. Starting from negative direction. So yeah, this is very important point to note here. If I add a right hand 0, what happens? Like all these things, right? I'm just telling you how you analyze the system, because this may come up in interview. Like questions you can easily solve just with a blink of second. In the gate question I'm talking about, the questions you can easily solve, the controllers and compensators chapter, because they are very easy. Just you have to analyze like where does the pole lie, what is the zeta, what is the omega, and like that you will be able to solve. We'll do that obviously, but this first lecture was about the interview things. Like if they ask something in the interview, how to analyze the system, what happens if I add a 0, what happens if I add a pole, what things will change, what things will happen. I am just like explaining you, I'm just teaching you how to analyze these things. If I add a 0, if I add an open loop pole, all these things, right? So here different systems I have plotted, like the system responses. For system 1, what is the system 1? System 1 is this this blue line. So initially my system response was something like this. Now I added a 0, okay, now I added a 0 which is much nearer to the origin. If I added a 0, sorry, which was, this was a system 2, right? This one was system 2. Yeah, system 2. If I added a 0 which is yeah, this one, if I added a 0 which is much, sorry, further away from the origin. If I added a 0 further away from the origin, yes, that rise time does increase, but not to that much extent. But here system 3, what is happening? Added a pole, added a 0, closed loop 0 much nearer to the origin. My rise time, you can see it just reduced at very first rate. So let me just explain. So this is initially, okay, system, I will just write this. System was like, let me name this as omega z0, omega z1, omega z2, and here my omega z is less than 0, okay. So this is my omega z where it is less than 0. So these are the three things. So here what is happening? So this is further away from the origin. So yeah, T rise does reduce, but not to that much extent. But if I add much more nearer to the origin, T rise reduces to a higher extent, okay, rise time. Now if I add a 0, close to 0, which is on the right hand side, what will happen? It will start initially from the negative, and obviously the rise time will be very high. So these are the things that happens. So this is not something we want, okay. This is not desired, that my direction will change, the response will go negative. We don't want this, okay. So obviously we avoid adding right hand zeros, okay. So yeah, in the closed loop pole I'm talking about. So here you can see this is the Bode diagram, okay. So from Bode diagram we can't like replicate much, because the phase, like one thing we can see that the phase like I was explaining in the Bode plot, right? So the magnitude plot will be same. So for system 4, like for system 4 I have added a port, system 4 and system 3, you can't see the yellow line. System 4 and yeah, system 4 and 3, they are just same. The magnitude plot are same because I added a pole in the same locations. Sorry, added a open loop 0 in the same locations. The magnitude plot are same, but the phase plot are different. Here you can see this is my system 4 and this is my system 3, okay, system 3. So they are exactly you can see that initially they are 360-degree apart, and now they are reducing, right? So yeah, the phase plot will change, but the magnitude plot will remain same. So that is what I was talking about in the Bode phase plot. Like we have already derived this. So like this is a summary of this like lecture basically. So like don't worry if you couldn't understand a few things, because what is the main point of this? The main point of this is to analyze this thing. Like if we add a open loop 0, if we add a closed loop pole, if we add this, then what is happening to the zeta, what is happening to the system parameters, and is my system becoming more stable, is my system becoming less stable? All these things you have to analyze. That is the more like main important part of this, how to analyze things. Just write the transfer function, just derive few things. Okay, don't just see things, like don't just remember the formulas, okay. So yeah, here like I've summarized things. If I add a open loop pole more nearer to the origin, zeta will reduce. Now if zeta reduces, it is directly proportional to the rise time. I'm assuming my omega n will almost remain constant, so my rise time will reduce and other things will increase. They are inversely proportional to zeta. Again, like just remember in terms of zeta. Now like all these things may come in handy in the examination. If I add a open loop 0 away from the origin, much more farther, open loop 0 I'm talking about, open loop 0, okay. And here I'm assuming that 0 is less dominant. So I'm talking about the case where 0 is more dominant, because in that point of view the calculation will be very difficult, okay, because if the 0 is more dominant, then the response will be the summation of those two, and it is very, very difficult to analyze that. If I add a 0 much further away from the origin, the 0 is less dominant, then my zeta will increase, okay. Here as you observe that effect of performance by adding zeros. So if I add a 0 much further away from the origin, what is happening? My zeta is increasing. Exactly. And I'm assuming that zeta is non-dominant. I'm not assuming for this case, because if I assume for this case, the calculation will be difficult, okay. And there is no point of that. That longer calculation, because gate won't ask this type of question, which will take very high amount of time, okay. So zeta increases. I'm assuming omega n to be constant. Hence t rise will increase and other things will reduce. Now if I add a open loop 0 away from the origin, like I'm not talking about this case where my open loop 0 is more nearer to the origin, like this case I'm talking about the away from the origin. So they are almost similar, if I add a open loop 0 away from the origin, as the 0 isn't much dominant. So the summation term, this summation term, right, the 0, as the 0 is not much dominant, this will almost tend to 0, okay, and this will not affect this response. So yeah, the case will be this. Just a quick summary, everything will be same. The t rise will reduce, as we see it is reducing here slightly it is reducing. Zeta will be almost same, but slightly it will reduce, and the other things will slightly increase. Not much difference, okay, slightly. All these things will slightly increase and decrease. Okay, so yeah, this was a summary. Now like another summary I have to the t rise performance. So like you can directly understand from this also. Just let's recall what we learned. So if my t rise, what will happen to my t rise if my zeta is increasing and omega n is constant? Like you can recall the formula. What was the formula? The formula was pi minus theta by omega d, okay, or I can write omega n under root 1 minus zeta square. Let me write this properly, okay. So pi minus theta by omega n by into under root 1 minus zeta square. So if my zeta increases, what will happen? If my zeta increases, this one will reduce. Zeta increases, this whole thing will reduce. Hence this whole thing is reducing, this whole thing is increasing. Denominator is reducing, numerator is increasing. That means this one will increase. So this one will increase. So rise time will increase. Now if my zeta omega n is constant, that means my omega n is reducing. Okay. So still if my zeta is increasing, so omega n is reducing, still this will overall will increase. Okay, this one overall will increase, because anyways the denominator is anyways reducing. Now what about my peak overshoot? The peak overshoot only depends on the zeta itself. It is inversely proportional to the zeta. So obviously if zeta increases, it will decrease. Here also it will reduce, because my peak overshoot is only dependent on the zeta. What is omega d? Omega d is depending on both. So this will be a bit difficult. If like omega n is constant, and zeta is increasing, what will happen? So obviously zeta is increasing, so omega d equals to omega n under root 1 minus zeta square. I'm just telling you how to analyze these things. Zeta square. So if zeta is increasing, obviously this whole thing will reduce, hence omega d will decrease. Okay, now what is happening to this? I can't say. Because here, if my okay, no, I can't say, actually, sorry, I can say. So if zeta is increasing, so this thing will reduce, but my zeta omega n is constant. Why is this constant? Because this is about the real part, right? Real part of where it is cutting. So this can tell us about the settling time. So if my zeta omega n is constant, then obviously my omega n will reduce if zeta is increasing. So here my omega n will, let me take another color, will reduce. So my omega n reduces and zeta increases. So what will happen? So obviously this is reducing and this is increasing, but this overall is reducing, so obviously my omega t will decrease. So obviously here also it will decrease. Okay, just try to understand how you can analyze different parameters. This is very important. Now what is happening to settle time? So obviously settle time is inversely proportional to zeta omega n. So here if zeta is increasing, then settle time will decrease. Here, as like settling time is what, 4 upon zeta omega n. So here zeta omega n is constant, so my settling time will also be constant. Okay, so yeah, this is the basically summary of all these things. Just this first lecture was to analyze different performance parameter and to understand what is actually happening to the system when we add poles and zeros. Okay, although like this will exactly not come into a gate examination, but this analysis will help you in understanding things further in much better manner. So in the next lecture we'll study about the controllers and compensators, different types of controllers, and after that we'll do questions. This is a very short chapter, not very long chapter, and questions come very simple, but you have to understand the theoretical part also. Okay, that is why I told you all these things, how to analyze things. So yeah, thank you for watching, and if you have any more queries you can ask in the Telegram group, and I will see you in the next lecture.